welcome you in the lecture series of random processes, detection and estimation. It is 18th lecture of this series. In the previous lecture, we have discussed detection of sinusoidal signal with unknown amplitude and phase. In this lecture, we will discuss detection of sinusoidal signal with unknown amplitude, phase, frequency and delay time. In the outline of this lecture, we will discuss detection of sinusoidal with unknown amplitude, phase and frequency, detection of sinusoidal with unknown amplitude, phase, frequency and arrival time. After this, we will discuss the concept of linear model. In the objective of this lecture, you will be able to explain how to detect the sinusoidal signal when there are unknown amplitude and or unknown phase, unknown frequency and unknown arrival time. And you will also able to explain why we use linear model in detection theory. Now let us start with the sinusoidal detection with unknown amplitude, phase and frequency. When the frequency is also unknown, the GLRT decides H1 or H0 if the GLRT, generalized likelihood ratio, means the PDF under hypothesis H1, which includes the estimated value of A, phi and F0, divided by the PDF under hypothesis H0. This is the generalized likelihood ratio, and it will be greater than or less than some threshold value gamma. We can estimate the value of unknown parameters by maximizing this likelihood function Px theta 1, means under hypothesis H1. By maximizing this likelihood function means the maximization of PDF under hypothesis H1 divided by the PDF under hypothesis H0, and this ratio will be less than or equal to some threshold value. And because under here the PDF under hypothesis H0 does not depend on the F0, so I have written only is Px H0. Now I can also write this expression as maximization with F0 Px A cap phi cap F0 cap H1 by Px H0, and so you have this expression here, and taking the natural log of both sides, you will get log E maximization of this ratio F0 Px A cap phi cap F0 cap H1 divided by Px H0, means PDF under hypothesis H1 divided by PDF under hypothesis H0, and this expression will be greater than or less than log E gamma. And from the previous lecture, you know, IF0 periodogram IF0 greater than less than sigma square log E gamma. This is new threshold value gamma dash, and from this expression you can write IF0 by sigma square less than greater than log E gamma. So here put this value log E gamma IF0 by sigma square. So you can find the expression from here, and from this expression to this expression. After comparing these two expressions, you will get the maximization F0 log E Px A cap phi cap F0 cap H1 divided by Px H0. It will be equal to maximization of periodogram with IF0. So maximum F0 IF0 by sigma square, and we can decide H1 or H0 if the maximization of the periodogram with F0 will be greater than less than sigma square log E gamma, and this means the new threshold value gamma dash. And the detector decides that sinusoidal signal in presence if the peak of the periodogram exceeds the threshold value, and the frequency location of the peak is the maximum likelihood estimate of the frequency. This explains why the periodogram or its fast Fourier transform implementation is the basic component in nearly all the narrowband detection system. And the detector decides that a sinusoidal signal is present if the peak value of the parallelogram exceeds a threshold and the frequency location of the peak is the MLE maximum likelihood estimate of the frequency. This explains why the parallelogram or its Fourier transform implementation is the basic component in nearly all narrowband detection systems. This explains why the parallelogram or its fast Fourier transform implementation is the basic component in nearly all narrowband detection systems, and its performance can be found in similar way to that the case of amplitude and phase unknown as we have seen in the previous lecture. The only difference is that the PF increase by the number of frequencies searched over, and the probability of detection it will be q x2 dash square lambda 2 log e n2 minus n by 2 minus 1 by probability of false alarm, where lambda is n a square by 2 sigma square. Here you can see probability of false alarm PF will be increased by the number of frequencies searched over, and the block diagram of the GLRT for sinusoidal detection with unknown amplitude, phase, and frequency. It will be we will compare the periodogram maximum periodogram with the threshold value. This means maximum of periodogram with frequency f0 it will be greater than less than some threshold value gamma dash. And IF0 from the previous IF0 from the previous slide, it is the combination of the xn and the exponential value of the signal or in the form of sine or cos. So it will be 1 e to the power minus j 2 pi f0 n. So first of all we have to combine these xn and this exponential signal, and then take the summation of this expression n0 to n minus 1. So it will be IF0, and maximization of IF0 you will compare this value with the threshold. So here the block diagram will be you have select the data, observed data, then the signal, exponential signal, combine these two and taking the summation of these two, and after taking the whole square of this, so IF0 here it is the whole square of this, so you will get IF0 and choose the maximum over f0. So you have to choose here maximum IF0 and compare this maximum IF0 with the threshold value gamma dash, and if it is greater than, then we will decide in favor of H1, and less than threshold value, then we will in favor of hypothesis H0. Now the sinusoidal phase frequency and arrival time unknown. In many situations, it is desired to detect a signal whose arrival time or its delay is unknown. For example, a radar system in which detection indicates an aircraft and its round trip delay is used to estimate the range. So the GLRT might be used as detector or estimator, and let the two hypotheses are H0 is corresponds to xn is equal to omega n, means only noise is present under hypothesis H0, and under hypothesis H1 xn is equal to s n minus n naught omega n, means is the delayed version of the signal Sn, where Sn is non-deterministic signal and n naught is unknown delay, and omega n is the white Gaussian noise with variance sigma square. The observation interval from 0 to n minus 1 should include the signal for all possible delays. And so now GLRT decide H1 or H0 if the PDF under hypothesis H1 which include the estimated value of the delay divided by the PDF under hypothesis H0. So it will be the generalized likelihood ratio, and it will be greater than less than threshold value gamma. Here n naught is the MLE of n naught, and n naught is found to by maximizing the likelihood function summation n is equal to n naught plus n minus 1 x and Sn minus n naught for all values of n naught. So the PDF under hypothesis H1, it will be pi n0 to n naught 1 by under root 2 pi sigma e to the power minus 1 by 2 sigma square x square n into pi n is equal to n naught plus m minus 1 by under root 2 pi sigma e to the power minus 1 by 2 sigma square x n minus s n minus n naught delayed version of the signal Sn and the whole square of this x n minus s n minus n naught and into pi n is equal to n naught plus m to n minus 1 by under root 2 pi sigma e to the power minus 1 by 2 sigma square x square n. So the PDF under hypothesis H1, it will be pi n0 to n minus 1 by under root 2 pi sigma e to the power minus 1 by 2 sigma square x square n into pi n is equal to n naught plus m minus 1 e to the power minus 1 by 2 sigma square into minus 2xn Sn minus 2 plus s square Sn minus 1, where n naught is between 0 to n minus m. So the likelihood ratio, it will be p x n naught cap h1 divided by p x n naught h naught. So the PDF under hypothesis h1 and PDF under hypothesis h naught, it will be equal to pi n is equal to n naught cap, means estimated value of the n naught, to n naught cap plus m minus 1 e to the power minus 1 by 2 sigma square into minus 2xn Sn minus n naught cap plus s square n minus n naught cap. Here you have included the estimated value of the delay n naught, and this ratio will be greater than or less than some threshold gamma, and taking the natural log of this, you will get minus 1 by 2 sigma square summation n is equal to n naught cap to n naught cap plus m minus 1 into minus 2xn Sn minus n naught cap plus s square n minus n naught cap will be greater than or less than log e gamma. But you know, summation n is equal to n naught cap to n naught cap plus m minus 1 s square n minus n naught. It is equal to summation n0 to m minus 1 s square n, and it is the energy of the signal epsilon. So the GLRT decide h1 or h0 if test statistic tx, means summation n is equal to n naught cap to n naught cap plus m minus 1 x and Sn minus n naught cap is greater than or less than epsilon by 2 plus sigma square log e gamma, and it is the new threshold value gamma dash. So the GLRT implements a correlation of xn with Sn minus n naught and compare with the maximum value. So the GLRT implements a correlation of xn and Sn minus n naught and compare it with the maximum value, threshold value. If the threshold is exceeded, then a signal is probably present, or you will decide the hypothesis H1, and its delay is estimated as n naught cap. Otherwise, noise only is declared if this is less than threshold value. So the test statistic can be written as Tx is equal to maximization of this expression test statistic with n naught, where n naught belongs to 0 to n minus m. So the tx will be maximization of summation n0 to n naught plus m minus 1 xn sn minus n naught, and maximization with n naught, which is belongs from 0 to n minus m. So the block diagram of the GLRT for signal with unknown arrival time. So first of all, you will have to take the signal and Sn minus n naught, because you have to correlate the signal with the Sn minus n naught. So, and taking the maximization and choose the maximum over n naught, and this test we will get the test statistic, because the test statistic is from previous slide, it is maximization n naught summation n is equal to 0 to n naught plus m minus 1 xn sn minus n naught, and then this test statistic is compared with the threshold. If this exceed with the threshold, then a signal is probably present, and if less, then the noise only declared in this case. So we will decide in favor of h naught if this px less than the threshold value. Now you know, if the amplitude, phase, frequency are unknown, the GLRT decide h1 or h naught if the px a cap, phi cap, f naught cap, h1 by px h naught greater than less than threshold value gamma. When the amplitude, phase and frequency and arrival time are unknown, the GLRT will decide h1 or h naught if px a cap, phi cap, f naught cap, n naught cap, h1 by px h naught. In this case we have not considered delay, but in this case when the delay is considered, so we will put in the PDF under hypothesis h1, it is n naught cap, means delay, estimated delay, where the estimated value of a from the previous slide, you know, it is a cap is equal to under root alpha 1 cap square plus alpha 2 cap square, and phi, it is tan inverse minus alpha 2 cap divided by alpha 1 cap. Here you know alpha 1 cap is equal to 2 by m, summation n is equal to n naught plus m minus 1 x and sn. Sn is cos 2 pi f naught cap n minus n naught, and alpha 2 cap is 2 by m, summation n0 to n, summation n is equal to n naught plus m minus 1 x n sine 2 pi f naught cap n minus n naught. So here f naught is the frequency at which if naught periodogram attains its maximum with a known n naught. So here the delay is known in this case, and f naught is the frequency at which this periodogram if naught attains its maximum. So I can write it as log e p x a cap, phi cap a f naught cap n naught h1 by p x h naught. So this is log likelihood ratio, and it will be equal to I n naught f naught cap divided by sigma square, where I f naught cap is 1 by m, summation n is equal to n naught plus m minus 1 x n, and sn it is e to the power minus j2 pi f naught cap n whole square. So to find the maximum likelihood estimate of NE, we need to maximize this likelihood function under PDF under hypothesis h1. So we decide h1 or h naught if the maximum of the likelihood function means PDF under hypothesis h1, and we decide h1 or h naught if the maximization of this periodogram I n naught f naught cap divided by sigma square greater than less than log e gamma. You can also write it as maximization n naught f naught I n naught f naught by sigma square greater than less than log e gamma. Or I can write it as some maximization of a parallelogram with n naught f naught that is less than or greater than sigma square log e gamma, and new it is the new threshold value gamma dash. Or you can write it as maximization of I n naught f naught, maximization of parallelogram with n naught f naught greater than less than threshold value gamma dash. Here I n naught f naught statistic is known as the short time parallelogram or spectrogram. So the GLRT compare the parallelogram for all delays, and then compare the maximum to the threshold. As you can see, it compared to the threshold, and if the threshold exceeds the maximum likelihood estimate of the delay and frequency is the location of the maximum, and this detector is the standard one in active sonar and radar. So the block diagram for the GLRT for sinusoidal detection with unknown amplitude, phase and frequency and arrival time. So it will be first you will have to take data, then correlate with or combine with the signal s exponential signal e to the power minus j2 pi f naught n, where f naught is between 0 to 1 by 2. Then take the summation from n0 to n naught plus n naught plus n minus 1. Then take the whole square of this term. You will get the parallelogram and compare this parallelogram where this parallelogram is I n naught f naught, and choose the maximum over f naught I naught and compare this parallelogram with the threshold value, and if it exceed the threshold value, then we will decide in favor of h1, and if it is less than the threshold, then we will decide the hypothesis h0 is correct. Now we will discuss classical linear model. A large class of detection problems can be easily solved by applying the classical or Bayesian linear model. In Bayesian linear model used for random signal detection, we can efficiently reduce the detection problem with unknown signal parameter to special cases of Gaussian random problem. For the classical linear model means deterministic detection, the GLRT is the standard approach. The linear model finds application in a number of real world problems and make the detection and estimation problem mathematically treatable. So let us take one example. There are two hypotheses. H0 hypothesis belongs to xn, it is equal to omega naught, means under hypothesis h0 we are only having the noise, and under hypothesis h1 we are having the signal a sn plus omega n, where sn is known and amplitude a is unknown, and omega n is the white Gaussian noise with the mean 0 and variance sigma square. The GLRT decide h1 or h0 if the PDF under hypothesis h1 divided by PDF under hypothesis h0 will be greater than less than some threshold gamma. So px a cap h1 by px h0 greater than less than threshold value gamma. Here a cap is the maximum likelihood estimated value of the amplitude A. So here we can write the expression, the observed data x is equal to h theta plus w. Here h is s0 s1 to sn minus 1 transpose, means all the signals are in the matrix H, and theta involves the unknown parameter. Here the unknown parameter is amplitude, so theta matrix involves A, and W is the Gaussian noise with mean 0 and variance sigma square into identity matrix I. So we have considered x is equal to h theta plus omega. And here H is S naught S1 to Sn minus 1 transpose theta A, and omega is the Gaussian noise with mean 0 and variance sigma square I, means covariance matrix is sigma square I. Here H is known as n is to p matrix. Theta is p is to 1 vector of parameter or set of the unknown parameters, and omega is n is to 1 random noise vector with PDF normal distribution with mean 0 matrix, and covariance matrix is sigma square I with the sigma square known here. We wish to test theta that satisfy the linear equation a theta is equal to b, where a is known r into p with r less than p matrix, and b is known r is to 1 vector. So the now hypothesis test problem can be written as H naught hypothesis belongs to a theta is equal to b, and H1 is a theta naught equal to b. Equivalently, we can write H naught hypothesis, it means xn is equal to a Sn plus omega n, where a is equal to 0, and hypothesis H1 corresponds to xn is equal to a Sn plus omega n, where a not equal to 0 and small n is from 0 to n minus 1. In the matrix form, I can write it as x h theta plus omega, where theta is equal to a, and matrix H is S naught S1 to Sn minus 1 transpose. So the hypothesis can be written as hypothesis H naught corresponds to theta is equal to 0, means a is 0, and H1 corresponds to theta not equal to 0, means the unknown parameter a is not 0. Also, I can write it as H naught corresponds to a theta is equal to b, and H1 corresponds to a theta not equal to b. Here a is the identity matrix and b is the 0 matrix. So far in this lecture, we have discussed about detection of deterministic signal with unknown parameters like amplitude, phase, frequency, and arrival time. Also, we have discussed the concept of linear model in detection theory. This was 18th lecture of the lecture series of random processes detection and estimation. In the next lecture, we will continue the discussion of the linear model. Till then, thanks for listening this lecture. Thank you.